have to learn it. The first one is the photoelectric effect, and so this thing here, a photocell, is kind of what we're talking about. And so inside that little old-fashioned ball of glass, there's like a half cylinder shaped piece of metal. Do you see that kind of concave piece of metal inside there? And so the photoelectric effect is when you shine light on a metal surface, electrons are emitted. We have to explain why that happens. And so inside that little glass tube there's a vacuum, and that's just to make sure that we can actually study the electrons without having them interacting with like. And so the other thing that's inside there is a little square of wire, and we use that to collect the electrons that are released. And so the curved piece of metal we call the emitter plate because it emits electrons, and the square bit of wire, or sometimes it's just a single piece of wire, we call the collector plate because it collects electrons that are emitted. And so when we're studying the photoelectric effect, we're just trying to shine different amounts of light onto a phototube and measure things about those electrons. So we're trying to measure things like the current, like how many electrons per second are being released, and see what that depends on. And we're trying to measure the voltage, and the voltage tells us how much energy is carried by each electron, because voltage is defined as energy per charge, and so we can work out how much energy each electron has got by measuring the voltage of the electrons coming out of here. So that's, in a nutshell, that's the photoelectric effect. And so we can connect our phototube up to this reflecting mirror galvanometer, which is like a very, very, very sensitive ammeter, and you can just see if you're kind of lined up right, there's a kind of yellowy glow by the zero there, which is it's kind of like the needle. It's a beam of light that shines, reflects off the back, reflects off here, and ends up finally glowing on the dial. And there's a little mirror that pivots inside here, and it pivots when there's an electric current that causes a little torque to act on, and it twists the mirror, and that's what makes the beam of light end up in a different spot on the screen. So it's like a sensitive way of measuring current. And so we're going to plug in our wee little photo tube, and when we expose it to the sunlight, can you guys, who can see that needle? Yeah. Anyone spot it? So it went from 0 all the way up to 7, and there's not a scale on here, like that 7 isn't calibrated to anything, it's just a number, like it's gone from 0 up to 7 on the scale. And so but it's proportional to the amount of current. So what we can see is that when there's very little sunlight shining, the current is 0. As we increase the brightness of the sunlight to very bright, it goes up to 7. If we move it into the shade, it's not quite down to 0, it's down to about 1.5. And so what's the link we're immediately making between the brightness of the light and the amount of current that's flowing?
The brighter the light, the more current?
The brighter the light, the more current that flows. And what brightness of light, like what do we think of when we're thinking brightness of light? What are we imagining in our physics model in our head? What does brightness look like for light?
Photons.
Physically. Okay, so if we're working with a photon model, what does that mean about the photons? If the light's brighter? More photons per second. And that's the photon model actually comes from this experiment here. So when we're trying to understand, like, how did people get their heads around this experiment, we have to think back to the wave model of light. And what does brightness look like when light's a wave? What does the wave look like if it's brighter?
Greater amplitude?
Bigger amplitude. And so when people were first doing this experiment, they were thinking, oh yeah, brighter light, bigger amplitude of wave makes more current. When they were discovering this effect, what they found that really surprised them is that it doesn't work with red light. On lots of metals, red light, like there's no current at all. And that's like a really puzzling thing to have, that how come it works with blue light, works with yellow light, doesn't work. What we might do is draw a diagram of this circuit here onto the board to just help us understand a little bit better what's happening so far with what we've talked about. And so, kind of what's happening is we've got the incident light coming in, and that's releasing electrons from the metal surface, which then travel across the gap. They've got enough kinetic energy to travel across the gap and get to the collector plate. Let's label up these, the emitter plate, collector plate, and the electrons. They are just electrons that are emitted, but to distinguish between these electrons and any other electron, we're going to call them photoelectrons, but they are just electrons. Photoelectrons means an electron that's emitted because of the photoelectric effect. And we can measure, we can count how many electrons there are down here with our sensitive ammeter. And if the electrons are going that way, which way is the current flowing around that circuit?
Clockwise.
Opposite.
Anti-clockwise.
The opposite way to the electrons. So if the electrons are going anti-clockwise, the current's going clockwise. So I said that they had to have enough kinetic energy to cross across that gap. Why would they need kinetic energy? So there were electrons on this metal surface here. The incident light has released the electron. Why doesn't it just dawdle across to the collector plate? Anyway, if it's released, surely it's released, right? Why isn't it surely released? Why would it get attracted back to the collector plate if it didn't have enough kinetic energy? Why positive? Where's the positive come from? Must be positive. Why is it positive? Actually, you take an electron away, you leave behind positive. Good. And so it has to have sufficient kinetic energy to cross the gap to escape from the positive charge that was left behind. And then all that happens is it flows around the circuit and gets back to the same place it was before. So that's kind of what we're talking about. The photoelectron has to have sufficient kinetic energy to cross the gap to the collector plate to escape from the positive charge that was left behind, because the originally neutral metal surface, if you take an electron away, it leaves that with a spot of positive charge on